let's start with a bit of a history, and I would like to start with an introduction on quantum metrology and quantum sensing. So it started a long, long time ago, over 3,000 years ago, already in Egypt. They were trying to somehow have a way to measure things. So this is when the metrology started happening for us. They defined something that was called the royal qubit, and they defined it based on the current ruler, which was a pharaoh. So defined it as equal to the length of the forearm that was measured from the bent elbow to the tip of the extended middle finger. This shows us actually a lot, because what we do today, we also follow exactly same rules they had then 3,000 years ago. There was a primary standard that was made based on the length of this elbow of the pharaoh that was kind of like sculptured in granite. Then they had the secondary standards that were made so that all the people that worked in the ancient Egypt could build something. So they made them out of sticks. And then there was an architect or some sort of a main person in the construction that was responsible to check all the secondary standards with respect to the primary standard, if they still measure, if they still have a proper length. And if it was not done properly, it was even punished by death, not to keep the standard. So they really took it seriously. And actually, yeah, that resembles a lot what is happening today, right? We have some sort of a primary standard, we do the secondary standards, and then maybe we no longer punish people with death, but if you work in a series like metrology, like for industry or for commercial metrology, you can still be punished with some legal actions if you don't pay attention to keeping on the units.
I just wanted to say, yesterday we had already developed some really nice interactive culture of people asking questions. There are 2 microphones, and I think if you are all right with that, we would like to encourage that today too. So ask questions, interrupt, and with comments and questions.
Okay, sure. Okay, so they had the standard, and then within the times, as times was passing by, there were more and more standards, because then they had independent rulers, and there they found themselves having like over 800 standards for the units. For example, in France only, just before the French Revolution, that was really not a good idea, because the many measurements units gave a lot of disproportions in the society. So then the people got annoyed, because they were charged, of course, based on the measurement unit to pay. So they started a mutiny, and they needed a one. And that's when the French Revolution happened. And during the French Revolution, one of the postulates they had with the king was to really unify the measurement unit. And that's actually how the SI system was born during the French Revolution in 1719. And that's actually the kind of a metric system we use today.
Are you saying that we're not motivated enough for our measurement systems?
Yeah, so for example, they had this primary standard of a metre. They kept it in Paris. Then they made the secondary standards that were relocated to all the towns, so that people can come measure their own sticks and have a metre standard. So this is exactly what they did in ancient Egypt, right? But now there was a one standard for the whole country, and all the countries that agreed to use the metric system. But then something even better happened, and the quantum revolution came. And then we started changing how we define the basic units, so that they are even more properly defined. They don't drift, and they are more accurate. And for example, we changed the definition of the length, and we started defining length with the frequency transitions in cesium. This is something we can really nicely measure, right? Then we also changed the definition of the mass. First, we had a standard that was telling how much is 1 kilogram by just keeping that in the as a prototype, which we don't see. Oh yeah, we see it, which held up to 2019, and then this is not a good idea, again, because it degrades over time. You can see that there is the deviation from the original mass within the years. So again, we changed the definition. Now we use Planck constant to define the kilogram, and again, the transition in cesium. So we started changing this old metric system definitions so that it's even more precise and accurate. And now the question is, can we do the same with sensors? So can we go from classical sensors to quantum sensors and benefit from this like we benefited for the metrology? So there are many classical sensors that we use, of course, and then they hit some technical limits, right? We are limited by the technology, but we can also go to quantum because the quantum sensors will be more accurate, more traceable, and more sensitive. So we want to use them, but then we have to pay attention to the quantum mechanics because those are quantum systems, so they will be affected by the quantum noise. And the second part of my talk today, I would like to discuss this quantum noise and quantum sensors. Okay, so yeah, is there a second quantum revolution that we can benefit from when we talk about quantum sensing? So the outline for the presentation is, I started briefly with telling you the introduction about the metrology in quantum sensing, how we want to benefit from the quantum technologies. And now, during the first hour, I would like to make some sort of an introduction to vapor cell physics, how we can use atoms, especially the ones that are in vapor cells, to do the quantum sensing. And then in the second hour, to tell you more about quantum techniques that can be applied to those sensors. So I will tell you about the quantum noise and quantum enhancement possibilities, and I will show you the use case of the optically pumped magnetometer, and in this context, I will explain those topics. Okay. So we start with introduction to the vapor cell physics. So first question that arises is why we want to use atoms as sensors in the first place. So they are perfect systems to make a sensor out of it because they are identical, they are reproducible, and no matter where you have the atom, it will always have the same energy level. So here on the right side, you can see the energy level structure for the rubidium D1 line, rubidium 87. It's a nice atom, it's an alkali atom, it has one valence electron. We use it a lot for sensing. And in any place we put it, it will have exactly same structure, exactly same transitions. So, and this is a system that will have no drifts, it's very stable, and the fundamental limitations of sensing with atoms will be set by quantum mechanics. And okay, and now the question is why vapor cells? So the talk is about vapor cells, and I would like to motivate why we would like to use hot vapors in comparison, for example, to cold atoms. So cold atoms are very nice systems. They are super sensitive. They are very precise, but they just don't exist. So in order to have them in the first place, you have to make them. You have to have the whole lab. You have the ultra-high vacuum system so that the background collisions don't kill your system. You need to have basically a lot of space because you need all the laser systems to cool the atoms down. You need the magnetic coils to trap the atoms. You need, if you want to go to even more high sensitive systems, to have an ultra cold clouds and BC, Bose-Einstein condensates, you will need a strong magnetic field gradients. You will need the strong lasers to make the optical traps. And it's actually an expensive experiment. It requires a lot. And then if you want to do a physics that, for example, is very sensitive to magnetic fields, like you would like to look for axions, for the dark matter candidates, for example, you would like to somehow shield it from the magnetic field environment. And trust me, it's not easy to shield this kind of system with respect to the vapor cell that is tiny and can be just put in the common spherical mu metal shield. So these are the disadvantages of using cold atoms. The advantages is, of course, is that they are sensitive, they have long coherence time, they basically don't move. Once you trap them, you have a nice ensemble that doesn't move. And hot vapors can operate at room temperature, or it's enough if we just heat them a bit. So even if in room temperature, the vapor pressure, the density, the number density of the atoms is enough to have a nice light atom interaction to measure whatever you need to measure. They are compact and scalable. They can have low power consumption. They can be low cost, and they are quite easy to shield. And they exist. So this is actually by far the best feature of the hot vapors. And if this is not motivating enough, Alfred Kassel got a Nobel Prize in 1966 for showing the optical pumping with a glass-blown vapor cell. And there is a really nice YouTube video you can see that tells about the memories of different people like Cohen Tanuji about Alfred Kastler. Okay. So there is plenty of applications for vacuum cells, for the vapor cells, and there is a separate talk, so I'm not gonna spend more time on it. I will just be briefly talking about a vapor cell in the context of optically pumped magnetometers. Okay, so what is a vapor cell? A vapor cell is basically a piece of glass that is empty inside and contains atoms. So what is important is that we have those two windows, and this needs a good optical quality because this is when the beam passes through the atoms. So what we want to do, we sense with the light, so we have the light atom interaction inside the vapor cell, and we measure the outcome of that through passing through the cell. So it's important that it's a good quality glass, that the beam can pass through, can be not distorted by it, and nothing changes with the light, and only the changes that are happening to the light are due to the interaction of the atoms inside. So for that, we would, for example, coat the walls of the vapor cell with an anti-reflection coating so that we don't lose any power of the beam. Then inside, what will be captured are the atoms, and this will be most likely the alkali vapor that is based on rubidium, potassium, and cesium. The glass cell, the vapor cell will most likely have some sort of a source of those atoms, which is usually a stem or cold finger. So this is basically the place in the vapor cell that contains the metallic alkali. Then we can heat it and we can increase the vapor pressure inside our cell. And the glass can be coated with a paraffin coating to mitigate the wall collisions, or it can have a buffer gas, and I will be talking about that in a moment. So this is our atomic sample. It's very nice. It doesn't require trapping. It doesn't require cooling. The atoms are just there floating around, and they are ready to be used for sensing applications. And it is nice because we can even use it in the room temperature.
Just want to say that putting them into a glass cell is some sort of trapping.
I very much like that idea, yes. Okay, so yes.
Oh, okay. Yeah. So, how do you put the alkali vapor inside that thing?
So there are different techniques and different kinds of cells, but for the glass-blown cells, as I understand, they put it just metallic, rubidium, for example, and then they close then they melt the glass on top, and it's there. But you can also use other techniques like dispensers or species like rubidium azide, especially in those MEM cells. So these cells are made differently. They are not glass-blown. There is a window, a cylinder and a window, and then you would put a rubidium azide, which is not a gas form, which is like a liquid form, I think. And then you would close it, and then it's not a rubidium yet, it's a rubidium and a nitrogen, and then you would activate it, and then it would compound. It would separate into a nitrogen and the rubidium, and then you would have it in the cell. So it's possible to put it inside before closing the cell because it's in the liquid form. And then when you close it, you activate it and you release the rubidium vapor. Or you just put a metallic part, like a droplet, like a milligram or even less of the rubidium or any alkali inside, like in a metallic form inside the vapor cell. And then you close the cell and then you heat it and you release the alkali vapor. I think these are the most common ways. And there are different kinds of vapor cells. There can be these glass-blown cells. There can be these anodic bonding microfabricated cells. I will maybe show one more slide about that. And then we have these alkali vapors inside. And basically what is happening inside this cell, so this is representing like the cross-section through the cell. This is the cold finger, and the atoms are just bouncing. And what you can see that the cells are quite small and the atoms are quite fast actually in the room temperature, or even if you increase the temperature, they're even faster. So they can reach the walls quite fast. This is actually representing the metallic rubidium or any other alkali. And then when you heat it, you release the vapor. And in the main chamber, you have a vapor, while the rest of the alkali is condensed here because you most likely would keep the temperature gradient. So you would have this part heated, you have a vapor there, and this would be a cold part, so the rubidium wants to be condensed there and don't go up. Or in the MEM cells, you could even have two chambers, one with the reservoir with that metallic part, and the other one that would be a science chamber that is heated. So
My suspicion is that your microphone is not on.
the question is, what is the difference between the left and the right figure?
So on the right, you have different cells with different geometries, okay? On the left, you have like anti-reflection coating on the, let's say the body of the cylinder, and on the two windows, you have
Sorry, so this was just a general description about this vapor cell in general, and some of them will have this anti-relaxation coating, some of them will not. Ideally, you would like to have it on both sides of the window. I think it's quite a struggle to have it still inside, so it will be from the outside, and there will be cells that are anti-reflection coated, and there will be cells that are not anti-reflection coated, because sometimes you don't need it. When you really care about the power of the beam that is transmitted through the vapor cell, because what you measure is absorption, you would ideally want to have as much light as you want. So we would put the anti-reflection coating not to lose 4% of the losses each time the light bounces, but not all of the cells would come with that. And I think usually you just send it to a company that can evaporate this anti-reflective coating layer. It is not made by a person who's doing, for example, this glass blown cell. And then some of them will have this anti-relaxation coating inside, and I will speak about it in a moment. And yes, they come in different geometries because you use them for different purposes. And for example, if you just want to shine a light through the vapor cell and measure that, you could use this kind of geometry. And if you would like to have some cross beams inside the cell, you could think that this would be better for you because you need good optical access from both sides. So you would ask for something like that. While the very old cell that is held by Alfred Kastler was just a round cell, because I think it's in general easier to make them, and then you shine and you just.
But for example, we have co-magnetometry cells where we also have helium-3 in there, and we create magnetization in the helium-3 using potassium or rubidium electron spins. And then the coherence properties depend on the shape of the cell, right? The spherical one has the best coherence properties if you have like a magnetized gas in there of helium-3 atoms. Because if it's not perfectly spherical, there are magnetic field gradients from the helium-3 that is sort of seen by itself. So the vapor sees itself and decoheres then.
I have a question. I think in one of your previous slides, you had a title of vacuum cell, and on this one, there's a vapor cell. So I was wondering if there's a difference.
Yeah, I'm sorry, it was supposed to be vapor cell.
Okay, got it. Thanks.
Sometimes they are also called vacuum cells, right? Because they are evacuated cells and they are buffer gas cells. So I'm not sure. Maybe it was on purpose or.
I just have one question as well here. Is there any particular reason for why you are only using group 1 elements like rubidium, potassium, cesium? Why not any other metals?
Why are we using alkali?
Alkali, yeah.
So so you always put inside what you need. So you need to think, why do I need a vapor cell? And if we do sensing, and I work, for example, with optically pumped magnetometers, it's good to have an alkali because of the valence electron and the interactions that are happening due to that. But also they use helium, for example, so you can also have a helium. I think it's a bit more challenging because it's easy to optically pump alkalis, but it's not easy to polarize helium. I think you have to do it with this discharge because it's not easily optically addressable. But you can put other species inside. And in fact, even for the rubidium cells, we put other species like noble gases or nitrogen that serves as a buffer gas. And I will tell about it like in a second.
Thanks very much.
Just one last question. These atoms inside the vapor cell, don't they interact with the silica of the glass wall and then impact the optical window?
So the question is, if the atoms that are captured inside interact with the walls? Yes. So let me go to the next slide. Okay, sorry. So let me just stop here for a bit. So this is what I said before, that we can basically increase the vapor pressure, but by increasing the temperature. And what is important here is that we will be able to reach different vapor pressures for different temperatures for different atoms. So you would also choose an atom based on at what temperature range you want to work. Sometimes you don't want to work with high temperatures because, for example, you are measuring a sample that cannot survive high temperatures, like some biological samples or bacteria or whatever. So you always choose an alkali or an atom to be suited to what you want to detect. And now about your question, wall collisions. Yes, this is by far the most bothering things when you work with vapor cells. Because of the wall collisions, you lose coherence. So, for example, we want to have a polarized atoms inside, and we want to use this strong magnetization we managed to induce in the system. And then every wall collision will lead to thermalization of the atomic spin states. And there will be many wall collisions because the atom will reach the wall very fast, actually in kind of tens of microseconds. So it's super fast. And this is a strong decoherence, and it will absolutely make the performance of our sensor worse because of that. So we need to find some mitigation for these decoherence mechanisms. And one of the different decoherence mitigation ideas is to use a buffer gas. So we have these alkali atoms that are captured inside, but we add on top of that buffer gas, and we can add basically we can think how much of a buffer gas we want to have. That will be pros and cons on having a lot of buffer gas and not a lot of buffer gas. So what basically happens, it slows down the atoms, it slows down the time until they reach the wall. They will be bouncing from the, for example, noble gases that are captured inside, like helium or neon and xenon, but those collisions that are happening with the noble gases, because the noble gases don't have the valence electron and we don't have any interaction between the electrons of our alkali and of the noble gas, are not destroying our coherence. And so this slow diffusion will keep our coherence at a good level, and we can improve the relaxation time up to 1 millisecond with such a buffer gas inside. What we have to pay is we have to pay the pressure broadening, because we put the gas there, we add 100, 300 or whatever we need torrs of that buffer gas, and this will result in the pressure broadening and in the shift of our signal that we measure. So this is what we have to have in mind, and this is what I actually said. So we have our rubidium atom, it has this valence electron, but then we have around a lot of helium, and we are actually not bothered by the interactions with them when they collide, because the spin exchange collision does not come with it. The spin exchange collision is when the two atoms collide and the electron cloud interact briefly but strongly, and we can have the spin exchange. And then this doesn't happen when you have a helium. So for that reason, we put a noble gas inside, and we have a low probability of spin exchange in this system. But we have more optical coherence. So but we have less optical coherence. We have more decoherence of the optical coherence, because when there is an excited state, they can they can interact and they can decohere to the ground state, and so we have more spin coherence, less spin exchange collisions, but we have less optical coherence when we add the buffer gas.
Let me just add that, sorry, because I talked about helium-3 a couple of times, and this is not helium-3, that's the normal helium-4. So there's no magnetization of that helium.
Okay, and then as a buffer gas, we can also have something that is not a noble gas, and actually very common one is a nitrogen. This works actually as a quenching gas. So there is another issue that is happening in those vapor cells when we have a very, very big optical depth, which means we have a lot of vapor pressure, we have a lot of atoms, then there is a strong absorption if we shine the light that is kind of resonant or near resonant, right? And then what happens that this resonant light does not escape the cell, and it suffers a lot of scatterings inside, right? Because the atoms absorb and then they emit, and then another atom can absorb it. And this also reduces the coherence. So, and as an effect, the cost we pay is this collisional broadening. And to avoid that, we add the quenching gas, which is a nitrogen, and then the photon that is emitted can be absorbed by a nitrogen, and it doesn't bother our coherence. Okay, and then there is another idea how to mitigate the coherence if we don't want to use the buffer gas. So if we don't want to use the buffer gas, we can also use special coatings that will prevent us from losing the coherence if the atom reaches the wall. And we don't see the atoms here. Sorry. So this one is coated with some sort of a special coating that will be a paraffin coating, or some sort of alkene or alkyne coating. And that thin layer of coating will have a special feature that if the atoms hit the wall, they don't actually hit the wall, they hit the coating and they don't lose the coherence, and they can bounce multiple times from this anti-relaxation coating and don't lose the spin coherence. And we can improve in such a way the relaxation time up to 100 milliseconds or even a second. And there is even a paper, this is the anti-relaxation coating. There is even a paper when they managed to get 77 seconds of the coherence time when they coated, which they measured in the alkane coated cell. What is the cost here is the temperature limit that you wanted to say something.
I just wanted to say that we have a cell that has 77 seconds, but then you showed the paper. So that cell is in the Helmholtz Institute. So I don't know where though. So, but it's here.
That's a long time. That 77 seconds is like a dream. It's very nice. What you have to pay here is the cost of the temperature limit you can get. So the paraffin coating and those anti-relaxation coatings, they cannot handle temperatures higher than, let's say, for example, in the case of paraffin, 60 degrees. This means you cannot heat up your sample. And if you cannot heat up your sample, this means you cannot increase the number density because you are limited by that melting temperature. So this is always a trade-off, right? You can have this very nice long coherence time, but you cannot have a lot of atoms. And a lot of atoms will help you to have a better strength of the signal for the measurement. So there is always a trade-off. There are some other coatings, like this OTS coating, that can be heated up to 170 degrees, but still it's not very very high. Some people will heat the cells up to 200 degrees or more. Locally. So in general, locally heat the atoms, you say?
I don't know.
So that's basically what we do, kind of. If you have this, for example, MEM cells.
I don't see why you don't remove all the gases from inside. Like, why don't you have a good vacuum inside and then heat it up so that the heat is not transferred to the walls anyway if you have a coating with paraffin or whatever?
So you would like to heat the, sorry. So first answer is you have to be careful when you heat the glass ununiformly because it can break. It doesn't like very strong temperature gradient. So that's one reason not to heat it very, very ununiformly. And what you're asking is when I have a cell, if I can heat only inside, not heat the...
I would imagine some filament which is very close to where you keep the...
That's mostly what we do. We put some sort of traces on the walls, on the windows, and we heat just running current through them. There are also some other ideas to heat the cells, I think, with the lasers. No, they are trying to do the laser heating. But this ununiform heating of glass is rather something you would like to avoid. And also 200 degrees is a lot. So one remark about this is that if you would like to have a very, very sensitive magnetometer, you operate, one moment, in something that is called a serve regime. These are the magnetometers that operate at a very low fields with a very big number density of atoms, so you have to heat it a lot. And for those, you always have to use the buffer gas because the paraffin coating can only handle like 60 degrees.
Can you repeat the question? I mean, like, what was it? Like, why don't you just heat the atoms or...?
That they have these coatings, and when they have this coatings and they can't heat the sample so that they can't produce more number of atoms. So I was asking if you can degas the entire, I don't know, vapor cell and then heat only locally where you have the sample and not the entire...
I mean, what will happen is that the vapor the rubidium atom goes from the hot place to the cold place and condenses there. So, I mean, it's like a material transport. It's also a heating mechanism, right? So it's not that you can choose locally which places you sort of heat and like the vapor is in thermal contact with itself, right? So, and with the walls and so on. So I mean, you make temperature gradients for things like that you avoid condensation, for example, on the cell walls, but that you can play tricks with the number density and avoid hitting the wall. I don't know. Don't see that. But Nia also had a question.
Could you say something about, I don't know, an intuition about how these anti-relaxation coatings work, as opposed to what happens to the spin with, uncoated walls versus coated walls?
So there is a very nice article by Georg Bison and Anne about how to create an OPM, and there is a chapter about that when they say that people say it's a black magic, how the anti-reflective coating works. I think it's not easy. I think the problem there is that there are some things we still don't understand. For example, you can have many anti-relaxation coated cells and they will give you different performance. I think what happens, there is this absorption, adsorption of the alkali in the wall, and then it stays there for a while. And how they measure, they actually try to estimate the number of bounces they can do from the wall until it loses the coherence. And standard, you have like 100 of those bounces for different coatings. For the super long 77 seconds, they will have like 1,000,000. But what is the physics behind this? I don't know.
I mean, we can ask Morgan, but sort of my intuition, which I was sort of happy with, is that those coatings are very long molecules, right? So super long chains of molecules. It looks, if you want, you have a collision with a hard wall as an atom, where it's just like a nothing wall, or you have something that looks like a seafloor with a lot of algae. So the very long molecules hanging into the room, so that the collision is sort of maybe happening slower. I have no idea.
But what does it do to the spin? I mean, what does the hard wall do to the coherence is for the spin, right? I mean, that's what we're thinking about. So what does it do to the spin for the hard wall and for your seabed? What happens?
I mean, in the seabed, the spin is just convinced to turn like nothing, right? The physical motion of the atom just is reflected. And if you have like fast things happening to the center of mass of the atom, maybe that changes the spin state. Maybe now it's time to bring in Morgan.
And you're not muted anymore.
Okay. Yeah, so this is a very good question, and I'm also not a great expert on this topic because I haven't really worked on the chemistry of this. And what Aleksandra said is true, that I don't think anyone understands very well what's happening here. But the picture which I've seen, which makes most sense to me, is that first, when an alkali atom hits the wall, then it tends to stick and stay for some time. And then it's in very close proximity to all of the components of the glass. And the glass is an amorphous material. It's going to have a lot of defects in it. So if it were perfect glass, then every electron would be participating in some kind of bond, and there would be no free electrons. But because it's an amorphous material, there will be defects where there will be some atom, which could be an oxygen, which could be, if it's the kind of glass that we usually use, could be boron, because that's borosilicate glass. And there can be defects that have a free electron spin. And that free electron spin is then in magnetic contact with the electron spin of the rubidium, and they very quickly do some kind of spin exchange. And in that way, the spin coherence of the rubidium is lost to the color center that it's close to in the glass. And what you get by coating with these long chain molecules is that they are, in some sense, perfect, defect-free. Every carbon is bonded to the right number of hydrogens, so that there are no unpaired electrons. And that then means that when the alkali arrives, even if it does stick to the hydrocarbon, then it does not have anything that it can exchange its spin with, or it has nothing that is close to it that it can exchange spin with. And so I think that's the general principle. But how well it works I think can be very complicated. That, for example, there are effects of diffusion of the alkali atom into the collection of hydrocarbon molecules, and I think there's plenty of research left to be done, and somehow evidence of this 77 is the 77-second result, because that was a surprise and it was much longer than coherence times that people had produced in other ways.
Yes.
Okay, and actually there were people who tried to do laser cooling to also mitigate the collisions with the walls. It also slows atoms down and reduces the coherence, but I didn't find many works on that topic apart from that one. They created a mod in a rubidium vapor cell. And that also allows you not to touch the walls, right? In those cold atom experiments, the actual cloud is like 1 millimeter inside of a huge chamber, so they never actually reach the walls. So there you don't need to worry about that at all. Okay.
Hi, I have a question. Sorry, I think I'm getting confused now. I think I didn't quite grasp the principle of a vapor cell yet. So are we trying to heat up the vapor, or are we trying to cool it down? I mean, there's this cylindrical shape which has the relaxation coating on both sides. So what exactly are we doing with the working principle, and what are we measuring?
So it always depends on your application. If you want to make a sensor and you want to have a strong atom-light interaction, you would most likely like to have a lot of atoms inside. Then you would heat your sample, right? Depending on the alkali or on the species you choose, you need to get to different temperatures. For example, with cesium, which is here with the purple line, you really don't need to heat it much to have a lot of atoms that will interact with light. So you would work around the room temperature. If you work with potassium, that is very nice because it gives you a narrow line width. You have to heat it. So then you want to work with biological samples, you would like to use cesium because you don't need to heat it much to have a good signal, right? Then if you want to have a very sensitive magnetometer and you want to have a lot of atoms to get a strong signal, you will work with something, then you will increase your temperature, right? But then you have a lot of atoms and then you have a lot of collisions, because the more atoms, the more collisions. So you start introducing this decoherence. So it's always a trade-off, and you have to find some sort of an optimal parameters for your operation. So what you would most likely do, you would have your cell, and then you would be measuring the signal, whatever you measure. For example, you measure the absorption of the beam through the vapor cell, and then you are trying to measure the sensitivity of your device. And then you would do it for many different temperatures, which means many different number densities, and you would find the optimal one. And then you would like to work in this number density optimal condition for your experiment. And depending on, for example, you want to work with low temperatures, then you will take an alkali that can have big number density at low temperatures, like cesium. If you don't care about that, you can heat it a lot. You can go to something that will produce more narrow line response, but you need to heat it more. But then with the very narrow line, you have a good sensitivity, right? Because you can measure more precisely. For example, your frequency of the system, if that is what you are looking for. So it's always a trade-off. And and what I wanted to say, yeah, so this is actually here. So, and then you have different atoms and they have different response to the magnetic field, for example. So if you want to measure the magnetic field, we want to work for magnetometry. We will also choose the species depending on what is the response to a change in the magnetic field. And then out of the, so there are two people who want to ask. Mm-hmm.
Maybe just like I mean, it's super cool that you're all asking so many questions, but she also has a full talk to give. So we have to, maybe we moderate a bit, right? And, or just keep it in mind. I don't want to quench the questions, but like we also need to get through the program somehow. So if you have a question that you can ask in the coffee break, that is also probably a good thing. I quenched the question. It's over.
Okay. So if there is something that stops you from following, please shout. Okay, yeah. So we will choose the arrangement accordingly, depending on what kind of temperature we can have. If we want to work with a buffer gas, or if you want to work with a paraffin coating, or if we want to measure magnetic fields or whatever, if we want to make a clock out of it, we will choose different species. So I'm mostly interested in magnetometry, and there are 3 candidates that people mostly use. So as I said, this potassium will give us narrow spectral lines, but it will needs heating. So if we want to work at low temperatures, we cannot really use potassium. We would choose cesium. But then with this high vapor pressure, we have a lot of spin exchange, speed destruction collisions. We have a lot of decoherence mechanisms. So it's, as I said, it's always a trade-off. And for us, we work with rubidium, but it's a joke. It's not just right. You can work with anything. What do you need? And then you actually not even always heat it, because, for example, for the mercury, the vapor pressure is so big there that some people even are, I think, cooling down mercury, because even at the room temperature, it's just too much, and then too much collisions. Okay, and then we have a choice. We can use microscopic cells, or we can use these microfabricated vapor cells. And again, this depends on your application. So they are nice. They are super sensitive. The big microscopic cells you have a lot of interaction. You have a lot of atoms, right? And the walls are pretty far, so you don't have that much wall collision. So you can have a bit of smaller vapor pressure, buffer gas pressure inside. You have less pressure broadening, and you can reach with those sub femtotesla per square root hertz sensitivity. Then if you need something small, because you want to make it more like industry friendly, you want to have a practical sensor that should be small, have a reduced swap, and be portable, then you could maybe be interested in working with microfabricated vapor cells. They can be like millimeter size. Then what you have to think of, again, wall collisions, because now the walls are very close. So then you would put more buffer gas inside. So again, you kind of try to design your vapor cell depending on your application. And here, the sensitivity people got is few tens of femtotesla per square root hertz with those microfabricated cells. And actually, what you can see here, I think it's a heater. So you would put, so for these microscopic cells, you build some, there will be a slide actually about the heater. So you build like an oven to heat it. And with those microfabricated cells, people can immediately like imprint the traces on the walls, and you can heat with that. Okay. And then, as I said, you can use those in the practical sensor. So this is a sensor that is developed to measure the magnetic signal of the brain, which I think you will hear a lot in the third talk today. And then this is a microscopic cell placed in the shields. There are 4 layers of new metal and a ferrite layer to shield it from the environmental noise, magnetic noise. And this is what we use in our lab to make like a fundamental measurements on this quantum sensor. Okay, and there are many people who work with those microfabricated cells, and this is a still developing field. So people are trying to really improve their performance to even get better sensitivity. And then for the heating, as I said, so for these microscopic cells, we would build some sort of a heater, and this can be either the DC heater or an AC heater. AC heater means that we heat it all the time with some signal at the given frequency that is not bothering us. And the DC heater, which, for example, I use, is done in such a way that I heat my sample for some time, then I switch it off, then I do the measurement, and then I heat again. And this is required because the heater introduces a lot of noise on its own, and these are very sensitive devices. So you need to operate when you don't heat. Okay, so about this temperature control, again, we want to heat them because this raises the number density of the atoms. This gives us stronger signal. So here you can see signal to noise ratio, how it goes up for different power of the light that we use to probe the atoms with rising temperature of the cell. But it also increases collisions, right? Because we have more atoms, more collisions. This gives us decoherence, faster relaxation. So there is always this trade-off between the signal strength and the coherence. So we always have this optimal number density operation. There was one poster yesterday with cesium when there was a map where they measured the temperature and probe power, and they found this optimal condition. So this is something you would most likely do if you want to have a sensor. And yeah, and this is the sensitivity that depends on the number of atoms and the relaxation time and the time of the measurement. So this is what we think of when we are trying to somehow design our sensor. Okay, and then if we want to use this vapor cell for the magnetometry, it's nice. We can fit it in the shields. We can shield it. For the miniaturized cells, we can now produce the heaters that will be around. We can produce the miniaturized coils that can provide us controlled test fields and the bias field. And I will be talking about the magnetometer in a moment. So these vapor cells are really friendly to make some sensor out of it. Okay, so it's a good atomic sample to make a sensor out of it. And this is a paragraph from this article that I mentioned to you about how to build your own magnetometer. So once you have a vapor cell, you want to first check that you have atoms inside, and you want to put the proper atoms that you want to work with. You need to make sure that you can have a decent density of these atoms so that you can have a strong light-atom interaction, you can have a strong response of the atoms. You want to, for the OPMs, you would like to be able to create the strong magnetization of the sample, and then you need to somehow mitigate the wall collisions. So you either have to provide a buffer gas, or you have to have the anti-relaxation coating so that you have a long coherence time. Okay, so now let's take a look in the context of magnetometers, what happens inside the vapor cell. So what happens inside the vapor cell with the atoms, when we apply the magnetic field, they will start processing in the magnetic field. So this is magnetic field, that is our bias field that we can generate inside the vapor cell. So again, I put the vapor cell inside the shields, there is no magnetic field around, I can precisely control it. And then I can generate the magnetic field in this direction, and then my spin will be processing around that, with the frequency that is called the Larmor frequency, which is proportional to the magnitude of that magnetic field and the gyromagnetic ratio. And this gyromagnetic ratio is what I showed here. There are different ratios for different species. So we would always choose the species of the ratio that you want to work with. And then what happens, the atom spin processes in the magnetic field, and we can describe it, we can look at this precession with a Bloch equation that describes the spin evolution, the collective spin evolution of my whole sample. So they precess in the magnetic field. And then we want to somehow measure this precession, because the fact that they precess is not enough, right? We have to somehow see that they precesses. So for that reason, we send the probe light through the vapor cell. So this vapor cell contains rubidium, let's say. Then we generate the orthogonal magnetic field orthogonal to the probing direction. Then we have a linearly polarized probe. And now what happens? This linearly polarized probe goes through the atomic ensemble. And if we have a good cell, nothing changes the polarization of that light other than the atoms. What we will see that the polarization of that light rotated. This is called the Faraday rotation, because of the atoms that are precessing in the magnetic field. What happens is that they create like a polarization dependent refractive index inside, and then our linear polarization, which is like a composition of a right and left circularly polarized light, right? They will have a shift, and they will get a different phase shift because of this different refractive index. And then what we will see that our linearly polarized light rotated after going through the sample, and it's not here. And what we measure how much it's shifted. So we have some polarimeter. In this case, what we have is a half-wave plate and the Wollaston prism. It just splits the polarization of light for two linear polarizations, and I measure the difference between those on the balance detector, which means I detect the S2 Stokes parameter. S2 Stokes parameter is the difference between plus 45 and minus 45 polarization of the light. So I detect this difference, which means I detect the difference that was induced by the atoms. So what I detect is the light on the balance detector, and that light have the imprinted precession of the spin atomic ensemble. So the angle of the rotation of the polarization will be proportional to the Larmor frequency of the systems. So by looking at the light, I can detect the Larmor frequency of my atoms, which means I can detect what kind of magnetic field the atoms are in. And this is what happens. So the atoms precess in the magnetic field. This is marked with this orange vector. And what we measure the spin projection on one axis, right? So my probe is here along this axis, orthogonal to the B field, let's say along the Z axis. And what we observe on the balance detector is this polarization rotation, which is actually like a spin readout along the one axis. So I see those oscillations, and the frequency of those oscillations is the Larmor frequency, and I can infer the magnetic field out of that. So this is what we measure on the balance detector. Okay, but then this is not the picture. That would be if there are no relaxation mechanisms, right? So that would be actually great. If there are no environmental influences, my spin coherence would be super long, nothing would be decaying, but there are relaxation processes in the vapor cell. There are those spin exchange collisions, spin destruction collisions. So when my atoms are colliding with each other, or if they are colliding with the buffer gas, I can have the spin destruction collisions, and I have these wall collisions that we try to mitigate either with a buffer gas or with the wall collisions. And all of them will be introducing relaxation to my collective spin spin polarization. And this is described here, and we add it to the block equation with some relaxation rate gamma. And now what happens, I put this gamma to have some magnitude, and what happens, initially I had my spin polarized along the z direction, and then while it presses, it starts losing the polarization because of this relaxation mechanism. So what I observe is something like this. This is what happens when we have a relaxation. Okay, but this actually is not a magnetometer yet, because this is not pumped. It was initially pumped here. And then we need to add a pump to our system. So what we add is we add another light, and we pump our atoms with a circularly polarized light. This is an energy level scheme again of the rubidium, and this is shown what happens if we shine the light that is resonant F2 to F2 transition with a sigma plus polarized light. You can see that we can only induce with sigma plus polarized light the transition that is happening between the MF levels different of +1, while the spontaneous emission can happen to the levels of MF equals 0, the difference MF 0 plus minus 1. So they decay here. So after many, many repeated cycles of this absorption and emission, what will happen? All the atoms will be accumulated here. This is so-called like a dark state, and we can no longer excite it because we shine the sigma plus polarized light, and there is no level these atoms can be excited to. And then in that case, we get a fully polarized system, and all the atoms will be in this F equal to MF equal to state. And now this is when we have an OPM, because we polarize the atoms and then we measure the polarization rotation. So this is what happens. In this graph, again, we have a spin readout along the z-axis. In the bottom graph, we have the corresponding pump. So we need to choose some pumping scheme. There are many different magnetometers, and the one we work with is called Bell-Bloom, which means we will be pumping once per cycle. Each time, the atomic spin will be along my probing direction. I will pump, I will stab, it will be very short, the atom will precess, I will pump again, it will precess, I will pump again, just to compensate for this relaxation. And this is what you will see here. And we add the optical pumping to our block equation. Okay. So I start with completely unpolarized atoms, because atoms in the vapor cell are unpolarized. They have some, this is like a thermal state. They are not polarized if I didn't do anything before with them. And now I start pumping. So what you see here, I start building up the polarization, and then the signal increases, the amplitude of the signal is increased with my each pumping cycle. And then I get some stationary state. And this is actually when I measure. Okay, yeah, so as I said, this is just one of the types of the magnetometers, but I will not be telling about the different kinds. So we just use this one that we pump once per cycle. Okay, so what we do, we gather the time domain signal of the spin precession in time, which is actually the polarization rotation of my light, right? Then what I do with this, I do the Fourier transform, and I can see at which frequency the precession has happened. And then what I do, because I use this pumping, I can demodulate the signal with my pumping reference. So I can basically like multiply with my pumping reference the time domain signal, and I can then get the signal after the demodulation. And this is what is interesting for us, because this tells me what is the noise in my system. So parts of the graphs I will be showing you is this noise around my Larmor frequency. So this is my signal. It's nice. Signal to noise ratio is actually very good. And then I'm interested about the noise around it. Okay. So what does this tell us? Let's see what happens if we have a resonant field. So when we have a resonant field, we pump when the atom, right, is just at the along the Z direction. If we have bit stronger field, so if we have, sorry, or no, weaker. So what happens if we have a weaker field? If we have a weaker field, no, I think it will be random. Okay, now, so if we have a weaker field, our pumping comes too fast, right? Because the pump is something I said. And then if it's too strong, the pumping will be delayed. So I will have so what I will have when I look at my signal after the demodulation, I will see that my quadrature, out of phase quadrature, will change because this too weak or too strong pumping, so not resonant with the Larmor precession, will change the phase or the amplitude of my signal. If I suddenly start pumping slower or faster, which means that the magnetic field changed, it's either stronger or weaker, I can detect this change in the magnetic field by looking at the amplitude and phase of my signal. So what I do, how do I look at this amplitude and phase of my signal? I take this raw time signal, I demodulate it with the pump frequency, and I immediately have the response, what is happening to the quadrature of my system. And here you can see how this quadrature changes when magnetic field has changed. And we get this strong response around the resonant. So here where we see 0, this is when my pumping frequency is exactly at the Larmor frequency. And then wherever it drifts, I see the response in this quadrature. So this is basically how I get the information from my magnetometer that the B field has changed. Okay, but this is not the sensitivity yet. So we measure the time domain signal, we perform the Fourier transform, we have the frequency response, and then we demodulate and we have the noise around the Larmor peak. And then this is just the polarization noise. This is just noise in my system, and what I need to modify it, I need to take into account what is the responsivity on my system. So this is not a part of vapor cell now. This is just like to explain how the magnetometer works. So I measure this responsivity, and what I do, I just send different test signals, and I measure what is the response. So I have my magnetometer, it works very well, and then I apply the test signal of 100 hertz, 150 hertz, 1 kilohertz, 100 kilohertz, and then I look what is the amplitude. And I see that I have a very good response around, that is close to my, that the test signal is of a lower frequency, and then it will drop. So I will be able to detect, this will kind of like define the bandwidth of my magnetometer, right? So what is the bandwidth of my detection? But I can tune this detection by changing the bias field. And then I can get the magnetic sensitivity. So in this case, this is not a very good sensor. It's few picotesla per square root hertz, but this is just to show you like the general idea about the magnetometer. So, okay, are we actually? It's, I think, a good time. So what we have from this first part is the vapor cell in general as a source of atoms for a quantum sensor. And then if we use vapor cells, we need to remember about the wall collisions because they are our biggest threat. They destroy the spin coherence time, and we have to mitigate it somehow. So we can either use a buffer gas, or we can use the anti-relaxation coating, or we could somehow cool the atoms down inside. And then once we have this, we can use our atomic ensemble that is contained in the vapor cell. For example, what I showed you is to use it with the optically pumped magnetometer, and then we can measure ultra-sensitive magnetic field, very tiny magnetic fields, because it's a very sensitive sensor. Yeah, and I think this is it about the first part. And
I think I mean, like, yeah, let's thank Aleksandra first of all. But we do have 20 minutes left for discussion, so all the questions that I sort of quenched could come up now if you want. Oh, there's another question over here.
So my question was, how clean the vapor cells need to be from inside before you deposit the paraffin on it? Or does it even matter, the cleanliness of the inner walls of the cells before depositing paraffin?
So I think what you care about in this case is that you want to have a good connection of a paraffin to a walls. And in general, what has been said about these vacuum cells, I think, yes, you want to have as good vacuum inside before you close anything there, because any other components that will be there and it will evaporate will be interacting with the light or with the atoms, even worse. With the light, no, because light will be resonant only with your atoms, but they can collide with your atoms, and maybe these are the collisions you don't want to. It's not as detrimental as with cold atoms, I think, because then you really need an ultra high vacuum to not have any collisions. But this is a bit more it can forgive you more when you have hot vapors, but still you don't want to have there any components that you don't need because of the collisions and yeah, any impurities will just decrease the coherence.
Okay, thank you.
Yeah, hello. Here. Yeah,
Here.
thank you for a nice talk. So can you again a little bit about how you're controlling the pumping and the rotation of
Yes.
amplitude?
Here for the magnetometer.
Yeah.
Okay, so what happens? Let's stop this. Can we stop this? Okay, let's put it here. So what happens is before you add pump, the atom will be still processing, right, around the magnet. That there will be like a still precession around this magnetic field, but this will be random, and this will be just random fluctuations. And then you add pumping, you polarize the atoms along one axis. And how you do it in this particular scheme is you shine a pulse of light that is circularly polarized. And here it looks like it's tilted, but in an actual experiment, we are trying to overlap them and have a pump that is circularly polarized with the probe along the same direction, okay? And then what we do, we try to pump the atoms when the spin is along that Z direction. And how we do it? By changing this frequency of the pump. So this pump is actually driven by a waveform generator, and I can choose the frequency of so I can either modulate the amplitude or I can modulate the frequency of the pump. Because what pumps my atoms is the resonant light. So maybe I will go back here. You meant this picture first? Or the technically how I pump? So what I want to have a resonant interaction with my atomic sample. So for example, I want to have a resonant interaction on this transition. I have my light, I tune it to this F2 to F'2 transition. So this is rubidium D1 line. So this means I need like 795 nanometer laser. This is by the way another reason why you would like to choose a specific alkali to have it in the vapor cell, because, for example, you have the lasers that can work there, and the lasers are cheap at this wavelength and so on. So you want to have this resonant light, you make it circularly polarized, and this makes this transition possible, that you transfer atoms from F equal 2 to F prime equal 2 when the MF, so the hyperfine, so the Zeeman sublevel changes of delta MF equal 1, okay? So if you are resonant with this transition, and actually in vapor cells, you would be most likely resonant with both because of this pressure broadening, you will cover both of the excited states, but it doesn't matter. What matters is that there is no state that is F equal 3, which means this state cannot be excited because there is no MF plus 3 that this atom could be excited to. And then when you have these multiple cycles of absorption and emission, the spontaneous emission that happens to those 3 levels, there are those 2 levels that will be decaying here. And then effectively all the atoms will be pumped here, all the spins will be in the state of F equal to, MF equal to, because after many, many cycles, nothing will be left here because nothing can escape this state. That's why we call it the dark state. And now how we do it by using the circularly polarized light, and we do it stroboscopically. We do it once per cycle. And we do it once per cycle because we want to probe here and we want to have a strong amplitude along this direction. And then we need to, this is actually important, to have this operation working well, which means in the experiment, what you do, you need somehow to control the time of your pump. Either you can modulate the amplitude or you can modulate the frequency. Because if you are very far of resonant, you don't touch that transition that can pump them all to the dark state, you don't care. So it can be also frequency modulation. And then you are trying to match the Larmor frequency with the pumping frequency. And you will see it because you will look at your photodetector, you will see at the amplitude of the signal, and you will be tuning the frequency of the Bell-Bloom pumping. This is called Bell-Bloom pumping scheme, so that you have the highest amplitude possible.
So, like, we have to both like change the frequency and amplitude, and we see the measurement, and that's how we.
Or you change
determine.
one. You can just put an AOM acousto-optic modulator that is able to quickly switch on and off, and you could have like for 2% of the duty cycle the light on, and you would have it only when the you would have it. One remark here is that the pumping is the driving force here. So if you look at this equation, the pumping is the driving force for your atoms. So the signal will be always on this frequency, but when it will become resonant with the Larmor frequency, this is like a resonant response. This is a system of a resonant response. Then when it's resonant with the Larmor frequency, you will see your amplitude goes much higher.
Okay, thank you.
Thank you for the talk. I have a technical question. Do you shine the entire cell with the lasers? Do you expand the beams first?
So that is a very good question. So when you have buffer gas and you have many collisions with the buffer gas and the atoms will be slowly diffusing, you can shine a light just through a part of a cell, and you will have a good response. I think with paraffin, people, if they want to have all the atomic ensemble fully polarized, they will shine the light that is as big as the cell.
And how much?
Consider? No, I think it's the other way around. So if you have a buffer gas cell, then you are just interacting with the atoms in the laser beam.
Yes.
And if you have a paraffin-coated cell, for example, the pump laser beam, the atoms are flying ballistically through the whole cell. And if you just pump, let's say, a tiny fraction of that, they will still see it, right? They don't see it all the time, but they will still be pumped. I think one of the first papers that I wrote with Dima is about precisely that, the averaging of atoms in a paraffin-coated cell because they ballistically fly through it of the pump beam, right? So it is no difference whether you have a 1 micromillimeter pump beam or a 10 square millimeter pump beam. It's the same thing, just the power matters.
And how much are the typical pump powers that are used in these experiments?
It also depends. So the pump power will affect your noise, will affect your measurement back action noise, will affect your measurement back action noise. So then what is interesting for you is what kind of quantum noise interplay you want to have in your system. This will be more about that in the second talk. To give you the orders of magnitude, we use microwatts up to milliwatts with the pump. But then there may be situations when you want to have a super, super strong pump. You just want to pump with one pulse, and then you want to measure an FID. And then people use very big pump power. So there is, I think, one paper by Romalis when they used, like, I think it was even a watt laser with a pump. Morgan, do you remember that one, the Gianvito paper? I think it was a very strong pulse of hundreds of milliwatts. And then they were looking at the FID, because the stronger you pump, the bigger the pump power, the different degree of polarization you're going to get. And if you want to have a fully polarized ensemble, it is a lot of power that you need. If you want to say something, you are unmuted.
Yeah, I believe that paper was about 3 watts of power, instantaneous power from the laser, but it was also quite broadband. And so I don't know what fraction of that is actually interacting with the atoms. So I think your 100 milliwatt number is probably a good number if you wanted to do that strong pumping with a single frequency laser.
For the talk, I have an incredibly basic question. Where in this magnetometer would the sample be put?
Where in the magnetometer the sample would be?
So in the magnetometer there, where would you put your sample?
So there would be, this is the lab experiment. There would be an optical table that we prepare our light as we need it. And then we would have a big magnetic shield somewhere in the optical table. And then inside these magnetic shields, there is placed this hot vapor cell. There is an oven. And then, we can see it here. There is an oven. And then inside an oven, we have a vapor cell. So this is oven. There is a small hole that the beam goes through. Inside that, we have a vapor cell. So what is important where you place it is that if you want to do magnetometry, that this beam, that this vapor cell is shielded, magnetically shielded, so that there is no noise from outside.
If you're trying to measure the characteristics of a sample, like a material, where would you put that relative to the vapor cell?
That's not what they do. That's not what they do.
Gosh, okay, sorry.
He wants to know, I mean, like, what is your magnetic field that you actually measure?
Okay.
What does it originate from?
So this, this here, there is no sample, but we have, for example, another setup when we have a vapor cell that is a microfabricated vapor cell placed inside the cavity to have a better sensitivity. And then on top of that, we put a sample with bacteria. And recently they managed to measure the magnetic signal from that bacteria. So then the question is, how close can you put a sample to a magnetometer, right? So for example, when you do this MRI, you want to be basically as close as possible, but because you want to hit that vapor cell a lot, you also don't want to burn someone's head. So there is always a interplay with that. You need to put something there to isolate it. This increases the distance, but basically you want always to put it as close as possible just because the signal is stronger.
I would like to ask why, what's the reason for the excitation laser to be circular polarized?
So we wanted to be circularly polarized because the transition rules for the circularly polarized light are such that they can work on the transition, that the difference between the MF states is +1. So you could use sigma plus polarized light, but you could also use sigma minus polarized light. And then this would be a dark state. But if you would the linearly polarized light, you would not have a dark state, because for the linearly polarized light, you would induce this transition and then this transition, and then you would not have a dark state here.
Thank you so much for the great talk. Hello. I mean, a bit of a tangent here, but I know you work a lot with cold atoms as well. And you mentioned in one of the slides that you could in general make, like, in principle, you could solve the decoherence problem with using cold atoms or laser cooling and stuff like that. Since you already work with it, what is stopping you from, I mean, why haven't you approached further in this way? And what do you think would be the primary drawback of such an approach?
So actually, we did this. So we do have the Bose-Einstein condensation lab that also works with rubidium atoms, and we have them. Sorry, I just go to that. So this is actually from our experiment. So we have the cold atom experiment. The atoms are captured here, and we have there the Bose-Einstein condensate, and how we operate it for the magnetometry purposes. We operate it as a co-magnetometer. So it's really nice. With the cold atoms, you can really resolve the F equal 1 and F. You can independently address F equal 1, F equal 2 atoms. And then what will happen? They will precess in opposite directions because of the gyromagnetic ratio that has an opposite sign. And then this can operate as a magnetometer. So what we have here also is like just for the hot vapors, we have a Faraday probe that goes through the BEC, and we measure again the polarization rotation after going through the BEC. And with that, we have a good sensitivity, and we want to use this magnetometer, this co-magnetometer. So what is nice here, why is it a co-magnetometer? Because the magnetic noise will cancel out. Because of this opposite precession. But what will not cancel out is any other interaction that is magnetic-like interaction, but doesn't, but does not cancel out because of this opposite gyromagnetic ratio. So, for example, we want to use this cold atomic ensemble to look, or rather limit the interaction range for finding the axions, which are the candidates for the dark matter. So we do use the cold atoms too for the magnetometry. We have a Faraday probe, and the operation principle is exactly the same.
Do you use rubidium or some?
Use rubidium, yes.
And the two isotopes are an advantage in your case.
So here we have two isotopes. It's not isotopically enriched source. We use dispensers, but the nature of cold atoms is that the atoms will only interact with the resonant light. So we can somehow take the one isotope we are interested in. So we are working with rubidium-87 just because of the laser cooling wavelengths we are using. So we don't work with two isotopes there. We work with one isotope there. Even though our source has two isotopes, we can separate the isotopes by just cooling and trapping one of them.
Is it better than, I mean, have you, is the sensitivity better than surf type, or have you, is it better than surf, from the surf regime, or are you maybe close to that?
I would say, again, it's different applications. Surfs are most sensitive magnetometers. They require high temperature and then low magnetic fields. So, for example, with surf, you cannot measure higher magnetic fields. There is one paper when they are trying to do surf by, I think, in higher Earth fields, like by compensating, by using an active compensation. But rather, you would use surf only for low magnetic fields and higher temperatures. And then surf works with vapor cells. The sensor can be miniaturized. This stands in the lab. This is huge. You cannot bring anyone's head there and measure any signal, or you cannot really put easily a probe there and measure something. And yeah, I would say this is more for fundamental research purpose, for the magnetometry, with like some fundamental research rather than the use cases, unlike the magnetometers that are made with the vapor cells.
I have one final question regarding this. Sorry about that. Do you see an effect of containment field, like the containment field? I mean, of course, you use laser cooling. Do you use any other containment, or do you see the containment field like on a, like as a Stark shift or
containment field?
When you want to cool atoms, essentially, do you see that field on the as a shift, or as a Stark shift, or any other
magnetic field? You mean contaminations, or
the containment field interaction? So let's say the laser the laser containment field. I mean, when you make like a pincer out of, I mean, you want to catch the atoms, right, to make them cooler. Do you see that field on the as a Stark shift or something like that?
So is this a question about measurement back action? So if the light that I'm using, for example, for probing, if it acts back on the atom?
Yeah, that of course we all always have it, but just the field containment. Do you see that during your measurement, as for the magnetic measurement? Does it adversely affect, or it's totally fine?
I don't know that word.